an excellent example of that, where we, as we call ourselves collectively the energy agencies, work with all of you, the Water Board, as well as staff, is on the once-through cooling policy. And that was, in our opinion, a really good collaborative effort that had a good outcome. We working with Jonathan Bishop and his staff in the Water Quality Division, as well as the board. I think we came up with a policy that recognized the need for, consideration of electrical liability, and as well as in addition to being involved in the development of the policy, we're also ongoing involved, as it's written into the policy, through the SACWIS. I won't try to go through the I know it though. Statewide Advisory Committee on Cooling Water Intake Structures. Thank you. So we have an ongoing role in the we have an ongoing role in that, along with the Water Board staff, as well as 3 other state agencies, in terms of the implementation of the policy. So I think it's just an excellent example of all of us working together, that we wanted to say, we really appreciate that. We appreciate the fact that the board has decided that it's important to have these workshops, and we appreciate the opportunity to be here. So look forward to having the same success that we had with working with all of you on the once-through cooling policy. So that said, just an overview of what we're going to talk about today. We're going to talk specifically about some of the analyses that we think are needed for a complete assessment. We're going to illustrate some of the concerns that we think could be there. I mean, further study is going to determine what this is, but certainly potential loss of capacity and flexibility of hydroelectric resources, as well as potential shift of energy production to periods of lower value, in other words, from summer to spring. And also, if we find through analyses that there is some need for additional resources to replace any loss of potential hydro resources, there is a long lead time to replace resources, typically a 7-year period from start to finish, from the time that you start to plan for a new resource, be that fossil or otherwise, to the time that it's actually built. Okay, let's go. So just some key takeaways that we want to have you get from this presentation. First off, the significance of how much we rely on hydroelectric power in the state. So from a statewide perspective, roughly 11,000 megawatts of the 61,000 megawatts of installed capacity in the state. That's about 18%. That's a significant amount of resources. It's our most flexible resource that we have. Within the California ISO's balancing authority area, we cover about 80% of the state, approximately 9,000 megawatts of hydro resources in the California balancing authority area, out of about 55,000 megawatts of installed capacity. So currently we are able to dispatch those resources, under a number of, we have to respect existing water policies, and so that somewhat constrains our ability to utilize these very flexible resources, and certainly, this water quality control plan potentially restricts that capability even more. And right now we've got really quite a bit of uncertainty over what the impacts are until we've further studied it. But what we really need is a clearly defined set of water flow criteria proposals in order to conduct the modeling assessments that we'll be talking about. I'll just add one other thing here on this slide that I don't think we have as a bullet, but I think one thing that we have to consider is that the grid is changing dramatically as we continue to integrate renewable resources, and what the grid of 2020 looks like compared to 2012 is significantly different. And so when we start to talk about studies, we can't just be looking at 2012, we need to be looking out to 2020. So I think that's important to think about. Well, I keep turning this the wrong way. So just a little bit about balancing authority areas. 9 balancing authorities exist within California. 5 are fully within the state, and 4 are centered outside of California. Essentially the western interconnection, there are 3 interconnections throughout the United States. There's an eastern interconnection, a western interconnection, and Texas. California is part of the western interconnection, and these balancing authorities are essentially areas that they actually, essentially it's a balancing authority is, the operator must, it has to manage supply and demand instantaneously, essentially. It says here minute to minute, but essentially it's an instantaneous balancing of load with resources. This is just a slide. I won't spend a lot of time on this, but it just summarizes the hydro capacity within various balancing authority areas, and you can see the amount that would be within this Bay Delta plan, about 7,500 megawatts in the state, 5,300 megawatts in the ISO's balancing authority. So just a little bit about, I'm going to talk just a little bit about some of the studies that we currently do, at least from the electric system perspective, and Dr. Jassie's going to get into more about the specifics of how we have to model hydro within those studies and how that affects those studies. So typically electric system planning has focused on energy and capacity to meet demand. But as we know, things are changing. Load uncertainty combined with increased penetration of variable renewable resources, they create a need for flexible resources in addition to just energy and capacity. And so flexible resources like hydroelectric resources have to cover the sudden production decreases from wind or solar. Of course, all of this is even further complicated by things like the loss of plants that are retiring due to the OTC policy, air regulations. We see that a lot in the LA Basin, and we're going to start seeing that more in other parts of the state. And then, of course, potentially loss of maybe some hydro, depending on the outcome of this process. So just, I'm going to go through each of these specifically, but different modeling approaches for specific purposes, for general planning, for resource adequacy, procurement authorization, et cetera. 5 primary types of modeling: supply, demand balancing, transmission system assessments, local capacity assessments, system simulation, and finally flexibility assessment. So supply demand balances, this is probably the simplest from a modeling perspective. Basically it's an annual process. You may see from us every year from the ISO a summer assessment. The California Energy Commission conducts a summer outlook, and really it looks at the summer and just ensures that are sufficient resources to meet the expected peak demand, plus a reserve margin of about 15 to 17%. That accounts for things like higher loads than forecast and resource outages. So we look at that for our balancing authority area. The Energy Commission looks at that throughout the state. Transmission system assessment. So I'm just going to take a moment here and talk about transmission planning process, which is, this is probably we don't have a specific slide on this. This is probably the best slide to talk about it. At least, for all balancing authority areas do this. I'll talk about the ISO's balancing authority process. Our transmission planning is a 15-month overlapping process. It starts in January of each year, looks out 10 years, and then it's taken to our board in March of the following year. So we conduct that transmission planning process every year. So at this point, we're finishing up what's the 2012-2013 process that we'll take to our board, but in January we're starting the 2013 to 2014. So always looking out 10 years. There are specific components to that. There's the most important, and that's really what these 3 bullets kind of point to, is the a reliability assessment in order to meet NERC and WEC standards. Those are the reliability organizations that we have to ensure that we meet those standards. We also do economic assessments as well as policy studies for things such as transmission needed to connect renewables, et cetera. So just stepping through the bullet points, these are more related to reliability, which, like I mentioned, is really probably the most important part of the planning process. Represents the electrical connection of generation and loads via the transmission system. We identify overloaded transmission system elements and local or region system stability criteria. And then once we've identified those, we determine what mitigation measures are needed, and that can be new lines, reconductoring, upgrading of existing transformers, et cetera. And the tools we use for that are power flow, which I believe is what was done on the San Joaquin portion of this whole plan, basically using what's called a PSLF power flow, and it really just looks at the peak demand, but we also do dynamic stability analyses. So the next set of studies to talk about are on local capacity assessment, and this is to determine whether there's sufficient in-area generation for transmission constrained areas. We have 10 of those within the state. The ones that are applicable to the Bay Delta project are the greater Fresno area, Stockton and Sierra. Essentially what a transmission constrained area is, what these studies identify is, since they are transmission constrained, there's only a certain amount of generation that can be imported into the area, so that we need, these studies determine how much generation is needed to be on to meet what we call 1 in 10 load and prevent any kind of load drop due to any kind of contingencies. There is I mentioned before, the Resource Adequacy Program. That's a CPUC program, and the requirements for load serving entities being utilities, are based upon the study results that come out of this. And again, in this case, the tools we use are power flow studies, dynamic stability analyses, and essentially the goal is to prevent any load drop from contingencies. So next set of studies, system production simulation. Typically in the past, we've used those for economic studies in our transition planning process. Now we are finding ourselves using it quite a bit for renewable integration studies. Essentially, that is the type of studies that are done for renewable integration. What those do are a number of things. Assuming certain load patterns and non-dispatchable profiles forecast how a given resource build-out would be operated to minimize operating costs while meeting the constraints, what the optimum imports are from other regions, GHG emissions, the hours of unserved load and overgeneration, and the optimum dispatch of use-limited resources, and hydro would fall into that category. What we do is we look at this for 8,760 hours per year. So we look at every hour of the year in these studies. The tool that we use for that, and many other organizations use this, is Plexos. It's a production cost model. And the metric on this is just ensure that you have resources that cover loads and reserves in every hour of the year. So it's down to every hour of the year, but while minimizing the operating costs and other dispatch criteria. So we've heard a lot in the previous panel, and we'll be talking more about it in our presentation, is flexibility assessment. So this is something that we've been talking about now more with, as renewables are integrated into the system, we need flexible resources in order to meet the variability of the renewable resources. So the focus is on whether the resources are sufficiently flexible to meet operating needs. And typically we've looked at meeting gross load, meaning peak load, and now with renewables on the system, we've got some graphs later in our presentation that will really illustrate this more. So it may not be clear now, but it will be once you see the picture. We now shift to looking more at a a net load basis versus gross load. And the flexibility assessment, it determines whether we can meet that net load with available resources. We find, well, we'll talk about it later on in the presentation, but we're continuing to evolve in the way that we determine what these flexibility needs are. Plexos is, again, a tool that we use for flexibility assessment. We just have in there as an example of a metric what a maximum continuous 3-hour ramp is. And again, as you'll see in the graphs later, where with net load, we see some ramping that we've never seen. We don't see now in the system, but we will in 2020. So this is sort of where we'll transition into what Dr. Jaski's going to talk about, and that is just how we have to integrate our planning tools, electric planning tools, with water flow modeling. And that, quite honestly, water flow modeling is probably the most difficult part of any of our production cost simulations or flexibility assessments. And this table sort of highlights for each of the studies that I just went through how what the interaction is there with flow criteria. So I'm going to turn it over to Dr. Jaski now.
Good afternoon. Mike Jaski, California Energy Commission staff. And as Dennis said, the purpose of this chart is to try to start intersecting these stereotypical analytic techniques that have been long used in electricity planning with what you're grappling with in this water quality proposal process. So this chart is trying to begin to intersect each of these 5 techniques with different dimensions that could stem from your proposals or the proposals that are being talked about in this process, and then the degree to which they actually we think that they influence the electricity system. And this is all prospective. Karen Trigovich approached the energy agencies in the spring and tried to solicit, our engagement in your process. And to date, we're sort of at this level of conceptually interacting our techniques and capabilities with your process. We have a very long ways to go to actually do any of this kind of modeling. This is only how it is we might go about trying to intersect our capability and your needs. And one of the most important missing pieces is for us to better understand the actual proposals that you want evaluated. Frankly, something as basic as the definition of unimpaired flow is still a bit elusive to me, and I hear parties speaking at these 2 days of workshops as defining it in different ways, and at least as my well, at least as I heard them, they'd have quite dramatically different consequences for the electric system. So, if we're going to evaluate even a wide swath of those different definitions, let alone, translating them into the percentages people are talking about, we have a whole matrix of candidate proposals that might need to be looked at. Your staff has done some analysis, I think supplemental to their initial San Joaquin analysis, that looked at generator head reductions. So this came out of a concern we had that their initial analyses weren't fully taking into account the loss of capacity. And Mark Gowdy has been helpful in showing us some analysis that reveals the degree to which there can in fact be head loss, which as some of the earlier presenters at these workshops said, is influences capacity, What's not yet so clear is the duration of hours at which those head levels can be maintained. So, and the ISO and perhaps also the utilities within the Balancing Authority of Northern California have criteria for whether or not they can count capacity based on how many hours it can sustain production at that level. So there's a combination of, you know, head levels and flow rates at that level that are necessary to determine, you know, the amount of capacity value for that resource. So it's not yet clear that there aren't capacity losses from some of the proposals. But, you know, they've assembled some data that are very helpful, and there's another step or two that could be taken there. They also conducted, as Dennis mentioned earlier, a power flow analysis using a contractor, I believe. Unfortunately, the focus of their analysis was whether there would be thermal overloads on elements of the transmission system, and that's not really the right question. The right question, you know, as Dennis has been saying, is those tools are used to determine the capacity requirements and the capacity value of resources and how those intersect with peak loads, and particularly as they get focus in these transmission constrained areas. So the local capacity assessment analysis is not yet been undertaken to the best of our knowledge. And we'll talk a little bit more in a forthcoming slide about some of the potential challenges that we identified just from looking at a simple locational aspect of where hydro resources are. Which reminds me, another fundamental unknown from our perspective, and the chart that Dennis used that talked about capacity values in the different river basins and overall hydrologic basins, is the extent to which your proposals involve all the upstream hydro facilities. We frankly don't yet fully understand whether your flow criteria proposals, you know, are limited to the RIM facilities or whether they directly or indirectly would apply to the hydroelectric facilities upstream from there. And I think we find it hard to believe that the upstream facilities wouldn't be affected even if they aren't directly part of your regulatory process. Of course, system simulation is one technique to reveal the nature of how your flow criteria and the shift of water from months where it's coming down the reservoir or through the watersheds from rainfall or snowmelt, and whether it can be retained in reservoirs for later use. That the previous panel talked about, you know, that's a modeling technique that will help reveal the consequences of that, and to our knowledge, alternative flow patterns haven't been assessed yet. And finally, flexibility assessments are, as Dennis said, an emerging whole new category, to some degree using some of the same techniques but looked at from different perspectives, and this whole issue of ramping resources up and down on multiple cycles per day, even as one of those charts showed, and the degree to which the sort of latent capability of the hydro system, even if hasn't yet been used exactly in that way, you know, it has that capability, and we may be potentially losing or diminishing some of that capability right at the very time that, as we push into the renewable era, we're going to need it, and when we haven't in the past. So I'm going to talk more in the next 6 or 7 slides about some of these areas in a little more detail. In the spirit of what your expert panel said yesterday morning, this is true confession time. Quite frankly, we don't have a very good understanding of the hydroelectric system. It's quite common that people identify a particular water usage pattern and just assume it in electricity planning studies. It is so complicated to do it right that generally it isn't done right. People sort through, you know, many years of hydrologic record and the associated generation that goes along with that, and they pick something that's adverse, or they pick something that's deemed to be average. And depending on your purpose, you might just use one of those patterns, hardwire it as an input into the model, and the model just works around it and dispatches thermal generation and other things that actually are subject to the dispatch algorithms. So building off this last bullet, evaluating your flow criteria proposals, you know, however many of them that we end up needing to evaluate, is going to require us getting a lot smarter about how the system actually works, and thus use that as the baseline for understanding what the proposals might do to change that. So focusing, oh, thank you. Focusing on capacity issues just for the moment. The basic question is always, is there sufficient capacity available to serve load? And of course, as I said before on that initial chart, the big question is whether the rating of the facility will be maintained, you know, under alternative flow criteria proposals. It's important to recognize that what we're doing there in assessing capacity value is not the same thing as deciding whether the power is going to be generated. There's a value to having the capacity available for use, even if it's not used to generate energy. And that has to do with covering contingencies from other resources and the general capability of most hydro resources to go from turbines not spinning to full power in a very short number of cycles. And that has very much value to the ISO or other system operators. Can you keep moving that? Thank you. So looking at energy modeling then, so another whole set of questions is, how much energy are we going to be able to get out of a facility over a given period of time? What, you know, the calcium model is configured to operate in months, so months is a convenient, you know, a unit of time to talk about. Clearly, the history of the industry is to store water behind reservoirs and delay the use of that water for generating purposes. As is indicated by the prior panel, there is a value to that deferral of usage, both in terms of reliability, using it when system peaks happen in July and August, as opposed to April, May, June, when the water comes. And there's a value question also, which is less of an issue, frankly, from the energy agency perspective than the owners of those individual facilities. You know, we're probably a little more reliability oriented, but is a really important dimension of this. We tend to divvy up resources into these three categories: run of river, which obviously there's little, if any, reservoir storage capacity there. Those that are dispatchable, and then in some limited instances, pump storage, which are generally artificial but sometimes natural. And in the production cost models that I'll get to in a minute, the algorithms for dispatching hydro for those resources that are dispatchable range anywhere from complex to simplistic, or even almost non-existent if you hardwire in a historic pattern, like I mentioned, actually has been frequently the case for many studies. I think I've already mentioned this whole idea of average and adverse patterns from history. One of the problems in modeling dispatch is the big disparity in operating costs, the marginal operating cost for hydro resource being, you know, near zero, if not zero, versus, you know, any other resource has got some sort of marginal operating cost. anywhere from lowish to extremely high. So combustion turbines, as was talked about in the earlier panel, you don't want to use those too much since it might be costing you, 15 or 20 cents kilowatt hour to crank one of those things on, and they just go from off to on, and they're not flexible in the sense of individual units. You have a whole string of them. You can turn different numbers of them on or off, but you're really getting them into an on or off situation. Other resources like hydro are much more inherently variable. So what are the consequences of changing the annual pattern of generation? Forgetting the first bullet for the moment, which I probably should have put last, clearly at the most crude level, some sort of 30 or 40% unimpaired flow criteria is going to move water from traditional summer usage to spring usage. What is that going to mean? It's going to mean less value. Loads are lower. Spring is a high production period from the northwest, so we can get a lot of imports that are relatively low cost. And just inherently, power generated in that period of time will have a lower value per kilowatt hour than in the summertime. And if we get to the point where in high hydro years or particular meteorological conditions that you actually get a big pulse of water coming down, you may end up spilling some of that water if flow criteria require that it just pass on through. So there will be an energy loss if that is to happen. And then, of course, climate change will possibly extend the range of conditions that has to be dealt with 80 or 100 years of hydrologic record. Not completely clear that climate change is going to create more extremes, but it may push us into a different proportion of that distribution than we're used to having. I think in the interest of time, I'll just skip that slide. So a little bit more about capacity ratings of facilities. At least our initial view of things is that we can't see how shifting water from summer to spring does anything other than decrease summer capacity, but it won't increase spring capacity because the capacity of the facilities are fixed. The only thing it can do is potentially lead to a different use of that capacity, maybe more energy out of that capacity, but not more capacity. So from a month-to-month perspective, we're essentially going to lose some amount of hydro capacity. The only question is it a little or is it a lot? I think our previous panel made the point that summer months are the traditional month of system stress. Peak demand has been the condition under which most planning's been done, but that's evolving due to the introduction of renewables and the intermittency characteristics of the most prominent of them, wind and solar, particularly photovoltaic solar, and that's introduced this whole notion of the need for flexible capacity, and we'll have the whole last portion of our presentation talking about flexible capacity issues. Resource adequacy is a requirement that was introduced beginning circa 2006 after the electricity crisis. Its initial focus was on assuring that the capacity that existed was made available to the ISO so that we wouldn't have withholding by market players. But it's about to begin evolving into the planning horizon so that we actually use that capacity planning dimension as a perspective in how we go about identifying the need for resource additions. Again, our previous panel hit some of these same points, but the options, if there should need to be replacement of capacity, are generally these. Natural gas power plants, which are clearly much more expensive than hydro and introduce both GHG emissions as well as the issue of criteria pollutants and finding offsets and all of the other interactions with costs that other players in the economic system have to deal with as well. Storage, again, hydro has been the preeminent example of that, and the industry is working hard to move into batteries and electrochemistry, compressed air kinds of devices with flywheels, all sorts of exotic technology, which is still at this stage very expensive and with unknown lifetime and sort of limited capabilities compared to the resources that the electric system has been used to having. And demand response, of course, is one of the options for moving load around. Again, has been predominantly focused on summertime conditions, peak demand, using air conditioner cycling, sometimes interruption of industrial customers to trim that load and reduce the need for peaking resources. But there's probably limits to which the end users can be expected to have their use of electricity interrupted or dialed down. Not quite sure, whether we can get beyond the current 3 or 4% to the 10 or so percent that some people are talking about as a goal. But that's at least a point of discussion, is can we get to that higher level, and what kind of technology might it take to do that. And I'm going to wind up with this slide right here that talks about some specifics of where hydroelectric capacity is located, how that matches up to other capacity in these areas, and some observations about the issues that may reveal. So here we're looking at things from a local capacity perspective. There are 3 of the 10 areas that Dennis talked about earlier that are ones where there are substantial amounts of hydro capacity. Generally speaking, these are starting in Central Valley cities and extending up into the foothills where the resources are, and they reveal sort of the pattern of the electric system having transmission from hydro down into the valley cities, and not very good crosslinks between these areas. That's why they're transmission constrained. So Stockton area, as an example, has a little over 200 megawatts of hydro nameplate capacity. The total capacity in that area is about 620. The ISO's analysis of local capacity requirements, which is what category C means, is a little bit less than a total capacity. So you might think things are okay. If we had a little bit of D rate of hydro, there wouldn't be a problem because there is already a margin there. But in fact, where that hydro capacity is in a sub-area within Stockton, which is already in deficit. So any reduction in hydro capacity in that sub-area will worsen that deficit. And what does that deficit mean? That means that the reliability in that part of the Stockton local capacity area is already worse than the standards. We're not satisfying it now. And if we reduce rating of hydro facilities, will be even more urgent to somehow or other build other kinds of capacity in that area. Same kind of story in these other 2 areas. Considerably more total capacity in the Sierra area than hydro, but the requirements are pretty high. There's already a deficit, so even the Sierra area as a whole could conceivably have a shortfall, a deficiency, even with not counting the sub-area dimensions that show up as
Mike,
red.
are these surplus and deficit numbers current numbers, or would they be numbers that would be effective once the renewable portfolio goes into place?
No, these are prospective for next year. So this is an analysis for the year 2013 that the ISO did in the spring of this year, and which was reviewed by the PUC as part of the resource adequacy process, and essentially the requirements from the ISO studies built into the PUC's resource adequacy for all load serving entities for the calendar year 2013.
Do you have any idea what the numbers would look like based on the time when you get to the renewable, completion of the renewable portfolio?
I don't think I am aware that
Because
ISO has
not gonna
done
affect you in
that.
2013.
We are just about 1 year ago, for the first time, pushed local capacity requirements out to the 10-year time horizon. We did that in order to evaluate the consequences of OTC retirement. So that was mostly focused on the coastal areas, Greater Bay Area, dealing with those old steam plants. So these Sierra Foothills areas were not examined, to the best of my knowledge, with that 10-year forward look. We only do it the 1 year ahead.
So would it be fair to say that these numbers are quite possibly a better scenario than you would have at the completion of your renewable, pardon me, your renewable portfolio demands?
Even simply from modest load growth, they'd probably get a little bit worse, because the motivations to build capacity in these areas are not very large. And one thing, let me say.
Can you explain what you just said? Motivation to
that we
build capacity is not.
We have, as the previous panel said, a sort of partly competitive electricity industry. We have the IOUs who were incented to divest themselves of the fossil units, many of them the OTC units that your policy deals with. They kept the nuclear units, they kept the hydro units, partly because the water usage aspects of them were so complex to think that they could be implemented in a competitive ownership setting seemed rather daunting. So PG&E, is the owner of a lot of the capacity we're talking about, and of course, all of the publicly owned utilities that NCPA is a representative of a big collection of. There are no mechanisms right now that direct generators to build capacity in particular areas. There are no incentives for generators to build capacity in areas where capacity is short, such as this chart reveals. So that's why we're considering pushing resource adequacy sort of assessments into the planning horizon, so that we can, in fact, start providing signals to generators to build where we need them to build. Right now they build where it's convenient and cheap for them to build, whether we want them in those places, whether we need them in those places or not. And a point not on this chart, but which might be parallel to these areas, is that the individual utilities that make up a balancing authority of Northern California may well have some of these same local capacity issues, particularly with SMUD and its ownership of hydro up in the foothills. We do not have the same access to detailed information from SMUD and the other publicly owned utilities as we do through the set of regulated entities under the PUC and the ISO. So there's an information gap that we can't fully address at this point. And with that, turn things over to Nat.
Thank you. I'm Nathaniel Skinner with the California Public Utilities Commission. And I want to talk a little bit about some of the ratepayer cost concerns, and then I'll be going through more detailed slides and presentation about the modeling, forecasts, and assumptions. So regarding ratepayer costs, reducing the flexibility of the hydro fleet is likely to have impacts on ratepayers. This is largely because the hydro fleet is in place, largely depreciated, and the operating costs are low to nothing. In terms of just the capacity question, because as Mike indicated earlier, the valuation of the energy is a much more complex process, but just straight up looking at each megawatt of lost hydroelectric flexibility will cost approximately $2 million to replace with a combined cycle or combustion turbine plant or other equivalent resource. So if there's 1,000 megawatts of hydro that's taken off the system, about $2 billion in capital costs to replace that. It's also likely that the replacement energy will be more expensive. And then lastly, there's also increased greenhouse gas costs associated with the emissions from the new fossil generating facilities. So basically a variety of different factors are likely to raise ratepayer costs to the extent that hydro production shifts in time or capacities are reduced. In terms of the flexibility to integrate renewables, aside from generating energy, hydroelectric facilities are dispatchable, respond quickly, and can provide the ancillary services of regulation, which was talked about earlier, but also load following, so the ability over the course of an hour to move up and down basically as load changes. Part of that load following definition is still being defined. For example, there could be a difference if it's 3 hours load following requirement or a 2-hour load following requirement, which then plays in with what the impacts of the flow restrictions are. And just that these particular flexibility studies are new. The first study efforts really underwent in 2010, and as the result of that 2-year process at the Commission, the ultimate determination was that the studies were too uncertain to be used for procurement purposes. And we're re-looking at it again in this long-term procurement cycle with modeling results expected in March or April of next year and final determination at the Commission by the end of next year. In terms of variability for the forecasts in July 2020, based on a net load perspective, there's essentially a range from about a peak of 40,000 megawatts to about 63,000 megawatts. This requires a shift from a gross load perspective, or what the total load is, to a net load perspective, where you would take away various resources such as wind and solar, which are non-dispatchable. Different definitions of net load may also take away the contribution of base load resources. Dispatchable resources have to be sufficiently flexible to ramp up and down to meet this net load shape. So based on the chart here, the morning ramp starts at around 4 in the morning and is either very gradual and concludes at around, that'd be about 8 o'clock in the afternoon, so a very long but gradual ramp, or a steeper ramp covering about 30,000 megawatts over about a 12 to 14 hour period. The one other thing is that as more renewables come online, we're seeing a shift in the time of the peak hour from about 3 o'clock today to about the twilight hours. So essentially, as solar starts coming offline, that's when the peak is starting to occur, so the most stress time on the system. Forecast dispatch needs need to be based on the net demand curve. This slide represents January 2020. And as you start calculating the impacts of what wind and solar do, you end up with a much different profile than we're currently seeing today. There's basically an initial morning peak ending around 7:30, 8 o'clock in the morning. It then declines as basically solar production rapidly increases, is maintained for a couple hours, and then rapidly decreases due to it being the winter. And so that then creates a second stressed period of time on the system where the net load has gone from about 26,000 megawatts up to about 42,000 megawatts, so about a 18,000 megawatt ramp, which starts to rival some of the ramps that we're currently seeing in the summer. It's creating additional stresses on the system. That may not be the single greatest time of overall stress, but it is indicative of our current forecasts regarding radical changes to the way the system is operated. In terms of the maximum monthly load ramp, currently the ramps are relatively consistent throughout the year. They vary a little bit from about 5,500 megawatts up to about 8,000 megawatts. What we're seeing is in the forecast for 2020, the summer ramps are maintaining roughly their relative duration and size, but the ramps are radically changing in the shoulder months, so basically September through March. So again, just a much different system is what we're forecasting in the future. To kind of summarize those points, supply variability is increasing at the same time as the flexibility of the fleet is decreasing. So the preliminary studies from the 2010 long-term procurement plan showed a need of about 4,600 megawatts of new flexible resources were needed once you retired the once-through-cooled power plants. The current assessments show that about 3,000 to 5,000 megawatts, because of the OTC policy, will need to be replaced in the LA Basin, Big Creek, Ventura, largely in the southern part of the state. But that still leaves a net deficit of the total amount of flexible dispatchable resources. What impact hydro production will have on this, we don't yet know. And just to illustrate is currently there's about 800 megawatts of wind and solar on the system. By 2020, that grows to 13,600 megawatts. So we are getting a lot more replacement resources, but those resources are variable. As was talked about a little bit earlier, conventional generation can take up to about 7 years, on the shorter end about 4 to 5 years, and if we pay a lot more money and do it really quickly, it can be done in only a couple of years, but that can basically have other unintended consequences of maybe the generation gets sited in a less optimal location, or we just have to pay a lot more money to get the capacity online. Other resources such as demand response, energy efficiency, storage, small rooftop solar, may take only a couple of years to get online, but we're still talking, generally speaking, a couple of years, not just months or days. In terms of the flow criteria proposals, it's critical to understand the full implications of the alternative proposals on the use and capabilities of hydroelectric. Again, the system operation exclusive of hydro changes is changing radically over the next 8 years. Hydro changes just add one more level of uncertainty and complexity to that. And I think, just to summarize on this point, the energy agencies will need a sufficient amount of implementation time to enable the electricity infrastructure planning process to identify, procure, and construct replacement options, particularly if we want to do it while minimizing overall costs and considering the other state goals and objectives. Thank you.
Do you have any additions to the natural gas, increased storage, demand response as sources, alternative sources to look for?
So there's many different sources. Touching on the local area question as Mike did, right now many of these programs are not geared towards having savings in a particular area for a variety of reasons. Essentially, all of the ratepayers in one territory are paying for these demand response and energy efficiency programs. So if they were focused in a certain area, there are kind of some overall justice questions raised with that. It is something the Commission is starting to look into, is how programs can be more tightly focused to help reduce overall rates. One other point I will add is that, again, this is a forecast for 2020. There are some assumptions embedded in there that could be changed. So right now, many of these programs are focused on the current peak reduction, and they haven't necessarily been refocused to look at what the time of system stress will be in the future, which could change the overall availability of those resources to meet that need, or it could be that there's more resources and that could lessen the overall reliability impact we're seeing. A good example would be electric vehicles, which are currently focused at shifting it away from the peak hour into the evening. But if that charging period was shifted to be the middle of the day in the winter where we saw that large dip, well, that could help by increasing load in the middle of the day, which then decreases that ramp.
One other question, if that's all right. And I'm sorry, this is just my curiosity that was piqued when you were talking about it. Dennis, I think it was in your presentation, and thank you all for the presentation. It was incredibly, I'm fascinated by energy, so it was really interesting. And I could almost think I understood some of it. No, it was retooling parts of my brain I hadn't used in a while, and I enjoyed it. You were talking about how hydro's 18% of our in-state, so it's 11,000 megawatts of 61,000 megawatts of in-state power. What's our total power use? Like, how much do we import at different times?
So, well, I can speak at least for California ISO's balancing authority area, and we cover about 83% of the state. Typically about 25% is
Out of state?
Net imports
And that's,
from outside the state.
so you got coal coming from the east,
No
and
more
you've
coal.
got hydro from the north? Or what is it?
Well, no more coal imports, but
Well, it's still happening now. It'll be gone, I know, but,
right.
yeah.
Yeah. But you know, we get imports from the north. Typically, that's hydro in the north.
Mm-hmm.
We get imports from the east.
And that's a mix.
That's a mix of different resources.
But not, yeah. And so, and what percentage do you think is hydro
About
from the north?
what percentage is hydro?
What percentage of the 25% is hydro from the north?
I
Don't?
don't know off the top of my head.
Sorry. Thanks.
Yeah, I was just going to maybe add to a question that Chair Hoppen asked of Mike, and that was, you know, you asked, well, looking out to the renewables in 2020, and how does the hydro affect it? And we were showing that table of the 3 local capacity areas. But keep in mind, the hydro in those areas, as much as he was trying to illustrate there, it's needed for local capacity needs. That's also part of what the flexibility resources are for the entire state. Because the flexibility needs aren't necessarily locational. There are locational needs in local capacity areas, but we can use resources from all around the state to meet the intermittency of the renewables. So I just want to make that point.
Well, right, yeah. If you, one graph that was missing from your presentation that some people like to show is just showing how big the WEC is. I mean, the whole western grid is huge in the interconnection, so,
The western interconnection.
yeah.
Thank you. Oh, Stephen.
While we have our colleagues here, certainly want to thank you for a very educational set of presentations, and a lot of the focus obviously is what the Water Board is set out to modify and how it might impact flexibility. I learned a new word, dispatchable. That's a good one.
Yeah, Word doesn't recognize it. We've tried I, A, we've settled on A.
We have yeah, right. You have to make those decisions. We have a few words like that too. We'll talk later. But at any rate, in much detail, and I have a lot of interest in, you heard my earlier question about timing, and how we plan and respond. And Dr. Jaski made a comment about the use of latent capacity. And my question revolves around, okay, we're concerned about what we might do and how it affect you. With the switch to renewables, I'm sure you've looked at this a bit, how does that impact water resources? That is, and I think you've spoken to it somewhat, but when we switch to net load, has there been an assessment, even qualitatively, about an additional demand on hydro resources as we get into 2020?
Yeah, so that's that 4,600 number that you saw in that last
Good.
slide, where
Thanks.
we've identified in 2020 approximately 4,600 megawatts of flexible resources. That's above and beyond what we have now. So I think the point on that slide was that if, in fact, whatever is decided upon is in terms of unimpaired flow, if that affects capacity of hydroelectric facilities and their flexibility in terms of when that is available, that just means that we would need flexible capacity from other sources, potentially conventional resources, which then affects GHG, et cetera. It just sort of all piles on itself.
An additional answer to your question is that the ISO production cost model set up that we drew a lot of these 2020 pictures from does, for the resources that, hydro resources that are classified as dispatchable, actually dispatch them. And I was trolling through the outputs of that data set, and it shows quite different dispatch patterns from one day to the next. But we essentially decided not to show those because they are so rudimentary compared to the reality of how hydro units are actually used, that it might be misleading. And that's unfortunately indicative of how we have sort of tended to assume the hydro system, you know, obviously with some variability from one year to another because of weather conditions, you know, is not something that we have been modeling with a level of detail that is going to need to understand the consequences of these kinds of proposals. You can't roll, you know, all the hydro facilities up into 3 or 4 big lumps and then dispatch those, you know, and have, you know, any degree of comfort that you understand what's really going to happen. And so there's just the capabilities of these models are there to try to improve upon the assessments, but the data and the effort to unpeel down to a level of disaggregation in that modeling so that we have some degree of comfort that it represents something approaching reality. You know, there's a lot of work ahead of us in order to do that.
I understand that you know, there's a lot of interest among particularly large power users who have access to a stream to use small in-stream hydro, small systems, sort of distributed hydro systems, somewhat like distributed solar systems. Are you looking at that at all, particularly for these kind of hard to get to areas, as potential? It's certainly not going to be controlled by the big agencies, but it could be used for filling in for large users that are in a particular place with good access to a river
Or a pipe.
or a pipe. That's true.
Yes, there. So California's renewable portfolio standard, first of all, draws a line at 30 megawatts. That's the hydro above that doesn't qualify as renewable, but hydro below does. So there's been an incentive to develop below 30 megawatt facilities for now, you know, maybe 2 or 3 decades. Some of that has happened, and a newish innovation is these in-conduit, you know, sort of impeller type systems that will generate some electricity. But generally, neither of those technologies are dispatchable. Those small hydro tend to be with minimal reservoir behind them, and so they're in effect what we call run of river. They just generate whatever comes through there. So they're not thought, they don't get very high capacity value, and they generate energy, but they don't contribute to this flexibility that we're emphasizing in our presentation.
But they do reduce demand. They could.
They produce energy, but how they match up to actual demand is not clear. Some of them even have daily flow variations that, you know, might or might not match up to when electricity load, you know, was at its highest. It's still an in-conduit type thing. We really have to study, you know, what the flow, you know, in that was. Is it uniform, you know, throughout the day, or is it,